in an experiment.
And we don't know yet.
Why is light so far?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This week, the star that could reveal a black hole's spin.
And will exoskeletons change the way we move? I'm Nick Petrichow.
And I'm Benjamin Thompson. A star zooming around the centre of our galaxy could help physicists unravel a long-standing mystery. Namely, how much is our neighbourhood supermassive black hole spinning? This week in Nature, researchers describe a star that orbits around the supermassive black hole at the heart of the Milky Way, called Sagittarius A star, or SAG A star. While researchers know a lot about this black hole, where it is, how far away it is, its likely mass, and so on, how much it's spinning has been hard to pin down. In fact, whether SAG A star is spinning at all is unknown, but given that everything in the universe spins, planets, stars, galaxies, physicists are pretty confident that it is. In fact, spin is built into the models of how supermassive black holes work. Things like the enormous jets of matter they fire out require spin in order to occur. But gauging precisely what an enormous black hole spin is tough. You can't see these objects, and so researchers have had to infer and estimate spin rates for them by other means. And so, working out how much our closest supermassive black hole is spinning should help confirm that black hole models are correct, and explain more about how the wider universe functions. And this brings us back to the star the researchers are writing about this week, which they call S301. To find out more about it, and how it could help in the search for SAG A star's spin, I called up one of the authors, Stefan Gillessen, from the Max Planck Institute for Extraterrestrial Physics in Germany. Stefan laid out a bit more about what makes S301 useful in this quest.
The star S301 is on a very eccentric orbit, and it has an orbital period of just below 9 years. That's also the fastest and quickest orbital period we know for any of those stars going around Sag A star. And it's not only the orbital period which is short, but in particular it's also the star which comes closest to the black hole of all the stars which we know. And by the way, that will also make it, at least for that moment when it's at that closest point, it will be the fastest star which we know. It will actually achieve a speed of 25,000 kilometers per second. That's a lot, right? I mean, that's going more than halfway around Earth in a second. I mean, the speed of light is 300,000, so that's like a 12th of the speed of light or something like that. That's quite impressive.
So we have this star then with an elliptical orbit, and at one end of the ellipse, it's very close to Sagittarius A star. How close does this star get to the black hole? Maybe in units that I can comprehend.
Yeah, of course, you can express it in kilometers. That would be a stupid number. But I think it's not that further away than Saturn from the sun. So it's solar system scale. And it essentially gets attracted by the black hole, falls almost into it, but just almost. And so in that process, it actually gains a lot of angular momentum, and that actually makes it then swing out again. So the total orbital timescale is 9 years, and it's only a week or so in which the star passes by the black hole.
And how might the orbit of this star help researchers figure out the spin of Sagittarius A star? How do these two things go together?
Think about a plane which is flying across the ocean and doesn't quite know that there's a hurricane. And all of a sudden, the plane will sort of feel a different force than what the pilot might expect. So the total direction this plane is flying will be a combination of its own speed and the one which is imposed on it by the air in which it's moving. The closer the plane is to the hurricane, the stronger the effect is. And very similar, S301 will feel the spin of the black hole, which is affecting the space around the black hole, and thereby it's not traversing through, let's say, flat normal space, but it's actually passing through a region where the space itself gives the object an extra kick, and thereby you get a different direction of flight. And that is essentially what we would like to measure.
So if the supermassive black hole is spinning, then it will add a nudge to the orbit of the star. And I guess depending on how much it spins, that orbit will be altered to a greater or lesser degree.
Exactly. So the degree by which it differs from the original orbit is obviously related to how quickly the black hole is rotating, but it's also related to in which direction is the black hole rotating, right? We don't know. And so if we talk about measuring the spin, we actually not only need to determine how quickly the object is rotating, but we also need to know in which direction it is pointing.
And so these are things that the star S301 might help you to figure out. How did you go about identifying that it was indeed a star? Your first inklings, I believe, were back in 2023.
Correct, yeah. So we saw the object in 2023 first in an image, and okay, we noted down there's an object. Next month we saw it again, the month after again, and it actually also has moved in a consistent way. And so it could well be that this would be a new star. And then, of course, once you have 3 points, you can sort of extrapolate where to expect it. The fourth measurement showed it where it would have been expected according to the first points. And then you start to build up confidence that actually the object is a star on an orbit. And okay, moving on from there, then the year after again was where it is supposed to be. And at some point, one has collected enough data that you can actually fully determine the orbit. And it turns out that that orbit was this very highly elliptical path. Now, one difficulty of this object is it's damn faint. So it's not that we can point our telescopes for 20 minutes and we get it, but we rather need to spend like a couple of hours, 3-4 hours of observing time under good weather conditions. And that is actually the limiting factor. So not all of our data sets are good enough that we can actually infer it. It's rare to have a beautiful 6-hour uninterrupted observing sequence where everything is fine and no cloud is passing and so forth.
So faint and far away, how did you see it?
So we employed a technique which is called interferometry, and thereby we combine the light from different telescopes. And these 4 telescopes we can actually combine together such as if they were a mirror the same size, the distance of the telescopes. And thereby you get an image which is as sharp as a 120-meter telescope would deliver. That sounds like magic, and this is really what interferometry is.
I mean, given its faintness and its distance, how confident are you that it is a star? Is there anything else that could produce that signal which could explain what you've seen?
No, I would not be aware of anything else. We see it at many wavelengths, and something which is shining in many wavelengths in the infrared is a thermal emitter. So the thermal emitters in the universe, that's just a very difficult word for star. Also, we see it compact. It's the point source for us. That means it has to be smaller than quite a number of things, and therefore we are very confident that this is a single point-like star.
So you've put forward your evidence then that it is a star. What do you not know about it?
Well, let me then first say what we even know. We even know the type of the star because we know its brightness. From that, we can conclude it is only possible that it's a main sequence star. So that means it's rather sun-like, and we can firmly exclude, for example, that it's a giant star because there's no star of that brightness. And the even more beautiful argument is such a star would be ripped apart on the orbit of S301. Only a main sequence star is compact enough that it can be on such an orbit. What we don't know is, of course, are there planets around this star? That would, of course, be very exciting to live on a planet around S301, which brings you every 9 years very close to the black hole. That would be a fascinating life.
Yeah, my goodness. And what else from a research perspective would help you home in on what's going on?
Yeah. So also what is, of course, extremely interesting is how does that star come into its orbit, right? And there's a mechanism which is called the Hills mechanism. So you have 2 stars which are orbiting each other, and then when they come close to a black hole, you can redistribute the energy in a way that one guy is unlucky, loses all its energy and is stuck forever around the black hole, and the other takes the energy and is flying out at a very high speed. These are so-called hypervelocity stars. And so this is the hypothesis how that star came into existence. And so immediately people have pointed out, oh, there's one hypervelocity star which we know that would be a perfect match for S301. It's hard to say whether that star actually is consistent. But yeah, I think the mechanism per se is interesting. and by far the best explanation we have why a star can come so close to a black hole.
And so your paper is out now with evidence that S301 is whipping around this black hole at the centre of our galaxy. How long do you think it would take to work out how much the black hole is spinning? You don't put forward any estimates in your paper. Is this just step one?
It's clear that if we observe 3 revolutions of the star, that should be obvious. So that puts us at roughly 3 decades, but I'm more optimistic than that because we will include in our measurements very soon also data from the 39-meter extremely large telescope, which is currently being assembled, which for that telescope should be easy to get a spectrum of the star. The moment we get a spectrum, we also get radio velocity information. And that will help a lot in bringing down the timescale. And I rather think that within 2 revolutions we will get it. So we have already covered a good 4 or 5 years now, right? So maybe 15 years, so a good decade is my estimate. That comes close to my retirement age. But maybe I'll make it.
So when the time comes that you've amassed enough data that you can put a spin on this black hole, what could this information be used for?
One of the things is if a black hole is rotating, it's not a sphere, but it gets squashed a little bit. Think of a tangerine, right? And that leads to a perturbation of the gravitational field, which we can predict. It's given by relativity. If you tell me general relativity is the correct theory and the black hole is rotating with that speed, I can calculate how much that squashing is. And that at some point should also be accessible to observations. That is, of course, a very fundamental test, because if the amount of how much the object is non-spherical differs, we know general relativity is wrong. Nobody expects that, but it opens an avenue to testing general relativity on something which has never been tested before.
I think several stories we've covered have looked to test Einstein's theory of general relativity, and thus far it's come through unscathed.
It's a pretty good theory, yes.
Well, more broadly, what could knowing the spin teach us about the broader universe, do you think?
If we can understand how this black hole is rotating, we can understand how the gas around it is putting itself in a certain configuration. And this also determines how much of the gas is falling into the black hole, so how much gets sucked in. And this is one of the processes, of course, which leads to the growth of black holes. So by now being able to more precisely understand how our local black hole here in the Milky Way works, we might well be able to draw conclusions on how other black holes are being fed. Surprisingly, this black hole growth is not only affecting the black hole, but it's affecting the whole galaxy, because during this eating procedure, there's forming these jets and they might blow away gas and then stop star formation in galaxies and so forth. So there's a whole feedback linked to the feeding of black holes, and thereby our measurement might lead to a local calibration point for that process. So you see sometimes these local measurements are the anchors for something which we need to understand very, very far away. And that could well also be here the case.
That was Stefan Gillessen from the Max Planck Institute for Extraterrestrial Physics. To read his paper, head over to the show notes for a link.
Coming up, how the latest exoskeletons may be a little different from their science fiction counterparts. Right now, though, it's time for the research highlights, read by Dan Fox.
Snakebites kill between 80 and 140,000 people around the world every year. One reason is that many of these bites happen in rural areas with insufficient access to antivenom. So, to find a solution, researchers decided to investigate how snakes protect themselves from their own venom. A team looked at proteins in the blood of the western diamondback rattlesnake, whose bite can kill a human. Tests have shown that one of these proteins, FETUA3, inhibits 3 kinds of toxin in snake venom. They found that on its own, this protein wasn't enough to save mice injected with venom, but a combination of different proteins, which can block bleeding and inhibit enzymes that break down tissue, successfully neutralized the diamondback venom and the venom of other distantly related snakes. The team says that the results warrant further investigation of FETUA protein mixtures for clinical use. You can find that research in Proceedings of the National Academy of Sciences of the United States of America. Boats travelling along the world's rivers and inland waterways accounted for nearly a quarter of all CO2 emissions from shipping in 2022, despite these bodies accounting for less than 1% of the navigable waters on Earth. Researchers analysed billions of ship tracking records covering more than 12,000 waterways. By combining this with information on vessel size and engine type, they were able to estimate the emissions generated on each river. They found that vessels on inland waters emitted about 164 million tonnes of CO2 in 2022. The majority of these emissions came from just 20 big, heavily travelled waterways, such as the Yangtze in China and the Rhine in Europe. The authors suggest that these hotspots could be effective places to cut emissions through the use of cleaner shipping technology. You can read that research in full in Nature Climate Change.
Next up, reporter Shamini Bundell has been diving into the world of exoskeletons. These devices could help augment human movement, and they may now be coming to a store near you. So Shamini has been looking into how they work, how they may affect us, and what they may look like in the near future.
Exoskeletons were once firmly in the realm of science fiction.
It used to be everybody envisioned the exoskeleton that could do everything. It was the Iron Man type exoskeleton that you wear and can do every task you want.
But over the past decade, advances in hardware and software have created a boom in exoskeletons for everyday use.
So what I feel is that overall walking feels more supported and therefore less fatiguing for me. So you feel basically your leg being amplified in the movement while you want to step.
Technology that was until recently confined to a hospital or lab is now on sale to the public. Could exoskeletons give people more freedom? Or will we become unable to live without them?
You take it off and you're like, oh, I'm a little bit slower, and then you feel slower.
As commercial devices improve, are we about to see the age of exoskeletons?
The next 5-10 years are going to be so much faster than the last 5 and 10 years in the field.
Exoskeletons may seem like a modern invention. You might think sci-fi-esque robotic devices that give you super strength, but they actually have a long history.
The oldest patent application that people have found happened around the turn of the 1800s, beginning of the 1900s. And the idea was to build like this spring device to run with so that it would let you run longer and bigger steps and use less energy. It was never built as far as we know.
This is Daniel Ferris, a researcher who started working in the field of robotic exoskeletons over a century after those designs were patented. But the very latest exoskeletons may actually have more in common with those 19th century models than you might think. But to find out how we got here, first we need to go back a few decades to the turn of the millennium. Technology had developed from the bowed wood, compressed gas and metal springs of the late 1800s to using steel frames and large motors. Researchers were focused on helping people who'd become paralysed by an injury or by disease. But this metal motor technology wasn't quite as slick as you might hope.
Number one, they were very big, massive, bulky. So if you want to change direction, it slows you down and it becomes very clear you're not moving in the same way. And two, they didn't have enough degrees of freedom. And the problem is it became very much like walking in a pool of water or even a pool of molasses. And so all of the early designs in exoskeletons felt like you were doing extra work to get it to move.
In the last decade, the hardware has improved a lot. The interest in drone technology has pushed motors to get smaller and lighter, which means exoskeletons too have become smaller and light enough for people to wear and move in without feeling like they're walking through molasses. But having the right hardware wasn't enough. It's no good having a lightweight exoskeleton that keeps lifting when you're trying to crouch, or moving forward when you're trying to go sideways. The software needs to be able to guess what you're trying to do, and reaching that point required another recent technological development.
The biggest advances that have happened in the last few years for exoskeleton have really come because of AI and machine learning. If you build a dictionary large enough of all types of movements, people walking, people running, galloping, skipping, stumbling, taking short steps, jumping, crawling, every type of human movement, and you build that, not a large language model, but a mega movement model with all of these different motions, you can start to train your AI to learn how to understand what those motions are and to predict how to move in the future.
And these advances mean modern exoskeletons look very different from the chunky robotic limbs of past decades. A lot of the necessary components can fit into a flexible belt.
And this belt is motorized, so it has motors, it has batteries, and the whole electronics is contained within the soft structure. The structure itself is made of flexible and, let's say, lightweight piece of clothing, so the people can wear it over their clothes.
This is Enrica Tricomi, a researcher whose PhD involved creating a soft, lightweight exosuit made mostly of fabric. The power comes from motors which pull thin wires that they call artificial tendons, connected to more fabric wrapped around the user's thighs. I called her up and she gave me a demonstration with one of her prototypes.
The motors are connected to a pulley, and this pulley wraps up the tendons. Maybe you can hear a bit the noise, but you can see that these two cables here, when I try to move, they pull up my leg, trying to amplify the motion, and therefore while walking I get supported. You can see here that while I move my leg, the motors they pull up the two tendons, so you can see the motor rotation depending on my movements. So the idea is that this completely depends on me, so if I stop, the suit stops, but if I walk, the pattern is recognized, and I get support through these two tendons that lift up my leg during walking.
The sensor data is interpreted by AI to figure out what the user is trying to do and how the suit should respond. Suits like these aren't designed to give people superpowers. Instead, they support and augment the movements that people are already making, giving a little boost or a spring in the step, just like those old 19th century patents set out to do. Enrica and her colleagues designed this to aid older people with muscle weakness, specifically for activities such as walking, climbing and hiking. They tested it on themselves first, before recruiting some volunteers for an experiment.
So we tested 12 individuals hiking at the Philosophenweg in Heidelberg, which is this panoramic trail that goes up to the hill. And this was tested for more than 1.2 kilometers in two different conditions, with assistance and without assistance. And what we generally test is through a metabolic analyzer, that is a mask that the person wears. We record the O2 and CO2 consumption over the trial, and then from there you can have an estimation of the energy that is required to perform the walking task. And we were able to demonstrate that over these 12 individuals we could save on average 18% of the metabolic energy that was required to perform the hiking activity.
Enrica's exosuit is an example of a shift in exoskeleton design and in ideas about who might want to use this kind of kit. Historically, there's been two main groups of users pushing development: the military and people with reduced mobility due to things like spinal cord injuries or multiple sclerosis. But according to Daniel, there's a new driving force.
We now have a third push, which is I'm getting just a little bit older and I still want to go hang out with my son or my grandson, and I want to go to Disney World and walk around all day, or I want to go backpacking with them, but I get tired. Why can't I have something like a walking stick that's a little bit more powerful than a walking stick, that lets me keep up with them and to go farther? And that consumer disposable income niche is also driving the market right now.
An exoskeleton or exosuit is now something that almost anyone could use. A lightweight and unobtrusive wearable device is much more appealing to the general public, and companies are taking notice. There are now devices for occupational use. One low-tech exosuit is made by a startup called HeroWear and uses essentially multiple elastic bands acting like an extra back muscle, made for people who are bending and lifting hundreds of times a day for work. Then there are huge companies like Nike getting in the game. They've announced the development of a new ankle exoskeleton with robotics company Defy, aimed at what they call everyday athletes, so that they can run more often or for longer periods of time. In China, a number of popular tourist locations and mountain trails have exoskeletons available to rent. And Chinese company Hypershell sells a robotic exoskeleton that they say reduces physical strain, amplifies strength, and preserves energy. So an exoskeleton may soon be coming to a store near you. But if we all start suiting up and allowing these devices to do a bit of our walking or lifting for us, what will happen to our own muscles? As these devices have progressed, researchers have wondered whether these machines are actually good for us. Could people lose the ability to move for themselves and start depending on an exoskeleton? Daniel doesn't think so.
Every time we've actually had long-term chronic use of exosuits or exoskeletons, people have tried to find evidence they're getting weaker. It doesn't show up. They're not overtaxing their muscles, but they're not using those muscles. It's a support. It's not a replacement. You're at an order of magnitude away from what you would need to cause widespread atrophy.
Enrica would like to do some long-term studies of her flexible exoskeleton to investigate this, but she too doesn't envisage it causing a problem.
So will this cause even more muscle weakness? Actually, the hypothesis is that it should not, because the idea is that because you'll feel less fatigued, you can compensate with the longer walking, or let's say possibly climbing higher, or especially for older people doing all those walk during the day that you would not do at all. So in the end you get this compensation by moving much more because you feel supported in the movements.
Daniel says the field is at an inflection point, and we're now seeing much faster technological development than in the last 5 or 10 years. So are we about to find ourselves in an age of exoskeletons?
You can go to an amusement park and check out a wheelchair. 5 years from now, it would not be surprising if you go to that same amusement park, you can check out an exoskeleton. I really feel like you are going to see people that are maybe on the edge of their mobility, the people that are getting older. They walk a little bit slower, but they want to keep up with their grandkids at Disney World, or they want to go to the park and go on a hike. They're going to start to realize, I can wear this and it doesn't hurt me and I don't feel as tired. And I think a lot of those individuals will take advantage of it in the coming years.
And Daniel's hoping that perhaps he too will one day be able to benefit from the technology that he spent so much of his career working on.
So I am 56 years old. I used to play American football in college, and I've had 12 surgeries. So I know down the road, I'm going to have problems with my hips and my knees and my ankles. I've already had one ankle replacement. So I would love to see an independent ankle, an independent knee, an independent hip that you could just swap out and put on when you want and go to the park or go for a run and not have that isolated problem with your joint be the limiting factor, right? I like the idea of offloading some of the work in the exoskeleton so that you have less problems with the muscles that are having to do the work to keep up with your everyday life.
That was Daniel Ferris from the University of Florida in the US. You also heard from Enrica Tricomi from the Technical University of Munich in Germany. For more on exoskeletons, we'll link to a feature article on the topic in the show notes.
And that's all for this week. If you'd like to stay in touch with us, you can. We're on email, podcast@nature.com, or you can find us on social media, @NaturePodcast. I'm Benjamin Thompson.
And I'm Nick Petrichow. Thanks for listening.